Hello everybody, and thank you for being here. My name is Noël Bijl, and I would like to take this opportunity to present to you some of the research and work we perform at In Summa Innovation. The work I present today has been performed by one of our interns and involves the first steps of investigating the effects of fluid structure interaction on aeroelastic behavior. Before I present the work, I will give you a short overview of our company, In Summa Technology Group. Well, so what's in the name? It is primarily a technology company on a diverse level. It started as a company focused on business intelligence and big data. Combining the two and being smart with developing software created insight in data and company processes. In Summa Innovation is the business unit that I work for. Our core business is engineering through CAE, providing software, support, training and engineering services in the Benelux area, Belgium, Netherlands, Luxembourg. In this region, we are the exclusive agency for Hexagon MSC software. Web Dashboard is a company founded in 2012, helping companies with easily finding, viewing and sharing Power Business Intelligence reports. Last but not least, Illumino, providing artificial intelligence solutions for personal development and support through deep learning, neural symbolic computing, human-machine interaction, and behavioral psychology. We have a small team, but they are great people to work with. The sales team consists of 2 account managers, Matthijs and Serge, supported by our marketing officer, Melissa. Both tech team and sales team is supported by our CEO Anton van Daal, our HR manager Inge, and financial guru Jurgen. The tech team, of which I'm a part, consists of over 100 years of CAE experience on a broad level. CFD, structural, multi-body dynamics, material engineering, manufacturing engineering, SPDM, machine learning, and artificial intelligence. Well, some background about me. I started with In Summa in May 2020 in the midst of COVID as a senior technical consultant. Before that, I had a pretty extensive career in aerospace, which was a bit to be expected as I attended Delft University of Technology, faculty aerospace engineering. After completing 2 chairs, materials and structures, I started my engineering career with Fokker Aerostructures. Pretty soon it became clear, and the opportunity arose, to be honest, that I had special affinity with FE modeling. Within Fokker Aerostructures, I became an FE specialist and finite element key user for the CAE tools present at Fokker Aerostructures. After the takeover by HxGN, I continued on as an FE specialist and functional application manager for the stress tools in the engineering department. In Summa Innovation has over 80 customers in the Benelux region, grossing over 2.5 million euros in revenue. And yes, my previous employer is one of our customers. Next to Fokker, we have Philips, Tata Steel, Goodyear, Toyota and ESA in our portfolio, just to name a few. Next to this, we partner up extensively with universities in Belgium and the Netherlands. Obviously, one of our partners is Hexagon, as we are the exclusive MSC software reseller in this region. So the topic of today, the effects of fluid structure interaction. Well, with the first release of the MSC CoSim engine in 2020, in our view, one of the tools we need for investigating fluid structure interaction, the user experience and benchmark data for the software was limited. Because In Summa Innovation considers the future potential of fluid structure interaction, a study was performed in which the performance of the MSC CoSim engine was documented. The goal of the study was to document the increased accuracy of 2-way fluid simulations compared to 1-way simulations when analyzing the aeroelastic behavior of a winglet in this case. The two-way fluid structure analysis was performed by the MSC CoSim engine, and the 1-way fluid structure analysis was performed by SC Converter, an internal tool with SC Flow. The CFD analysis was performed by SCFlow, while the FEM analysis was performed by using MSC Nastran. The high fidelity application we selected for this investigation was a winglet. The primary goal for a wingtip device like a winglet is to minimize induced drag. Wings have a natural pressure imbalance by which they generate lift. A consequence of the imbalance is the tendency for the flow to curl around the tips of the wing, generating wingtip vortices. These vortices drag local stagnant air into the vortex, creating downwash. The downwash at the wingtips causes the local angle of attack to increase at the tip. The increased local angle of attack is what generates induced drag. Wingtip devices work by redistributing the vortex around the winglet away from the wingtip. The wingtip devices introduce secondary vortices along the trailing edge that dissipate energy from the main vortex, reducing main vortex intensity and rotation speed. Notice the reduction in intensity of the wingtip vortices in the figure we have below here. This is for a situation with a winglet where the color red indicates the intensity. The more red it is, the more wingtip, the more vortices are present. Here in the case of a winglet, you see, well, it's almost pink. In this case, where there is no wingtip device present, you see very red indications here on the wingtip. When I entered this study, I was actually not aware of so many winglet types. You see 4 types over here. Maybe there are more, but these are 4 we identified. The wingtip fence, mainly in use with Airbus on the A300, A310, A320. It actually acts really as a fence blocking the vertices. You have the canted winglet. That's a winglet that has been in use for quite some time actually. It was introduced on the 747-400 in the 1980s. Well, maybe over here you already see that A350, which is one of the types that Airbus is producing. It's a blended winglet, so it's actually a very nice shape transferring from the wing into the winglet. And a split tip winglet, where you basically have a combination of a canted winglet with a smaller winglet here below. The research was conducted with several boundary conditions, several conditions actually. The takeoff conditions was created due to the prevalence of induced drag at takeoff and climb out. When looking at the figure, it can be seen that the majority of the total drag during takeoff is generated by induced drag. An increased understanding of the structural deflections can result in design optimization. The boundary conditions are defined from an A320, taking off at maximum takeoff weight at sea level. The rotation speed was retrieved from an A320 flight training manual and placed at 156 knots or 80 meters per second. During the rotation, 5 alpha was assumed as rotation angle for the aircraft. Further variables such as density, dynamic viscosity, temperature were retrieved using the international standard atmosphere at mean sea level. The other condition, the cruise condition, was considered due to the time spent in this phase of the flight profile. Depending on the flight distance, up to 86% of the total flight time is devoted to cruise. The expected advantage for the two-way analysis in this condition is the prediction of the Mach shock wave location. After a shock wave, large pressure gradients occur that cause a significant increase in drag. The shock wave locations are based on geometry. Therefore, it was expected that with the two-way analysis, the location will be predicted more accurately. Data for this condition was taken from an Airbus A320 cruising at Mach 0.78 at 37,000 feet. Cruise speed and cruise altitude are derived from an A320 flight performance document. Environmental variables such as the speed of sound were retrieved using International Standard Atmosphere at 37,000 feet. The cruise angle was a difficult one to retrieve, but for this condition it was placed at 2.5 alpha. The alpha was used in cruise by a Boeing 757 actually. Although the 757 is larger and heavier than the A320, we use this data due to the lack of publicly available data for the A320 in this condition. So the analysis models we used for both one-way analysis and two-way analysis. In SCFlow, a flow domain was added around the winglet. Let me turn on the pointer. This is basically the flow domain around the winglet. Here, small, you can see the winglet. The domain will function as a fluid region and was sized based on the chord length of the winglet. As found in a validation study we've performed, it was recommended to have at least 15 times the chord before and 20 times the chord after the winglet. However, due to the size of the root chord being roughly 1.7 meters, it was decided to reduce this flow region to 6 times the chord in front and 8 times the chord behind the winglet, as calculation times significantly increased. The effects of reducing the flow domain become significant above 6 alpha. So because the conditions do not go above 5 alpha, the negative effects are minimal and deemed acceptable for this study. The root of the winglet was placed to the wall of the fluid domain, and placing the winglet to the wall eliminated shear flow over the root of the winglet. This is important as the winglet was clamped on this location in the FE model. The walls for the model are defined as follows. The right image over here, the below image was used as a reference. So free slip on opposite walls in the ZX on the ZX plane, velocity vector inlet on the left, top and bottom, pressure outlet, so outflow conditions on the right foil, and the airfoil itself is considered as an obstacle with a no slip wall. The wall mesh size was calculated with a desired Y plus value of over 30. This desired value of 30 was to greatly reduce the calculation time. The Y plus of 30 was considered the best balance between calculation time and accuracy, as the deviation from Y plus is about 5% with every step you take in Y plus when analyzing the lift coefficient and the drag coefficient. So in a perfectly modeled winglet, both the FEM and the CFD mesh would be a one-to-one to each other. In this way, forces can be directly mapped from the CFD mesh to the FEM mesh. However, given the CFD mesh is generally much denser than an FE mesh, interpolation or extrapolation is used to create pressure gradients between FEM and CFD. Depending on the size of the FEM mesh and the pressure gradients, results can vary widely. To quantify the effects of mesh density on the transferred force, a mesh conversion study was performed in which several meshes of varying densities are compared. Each mesh was assessed by comparing the resultant forces before and after the mapping process. Using this method, pressure losses during the mapping process can be quantified. As a baseline, the force in the X, Y, and Z direction were calculated by SCFlow. With the use of SC converter, these pressures were mapped to the Nastran mesh. The mapped Nastran mesh was subsequently analyzed using linear structural analysis, providing the resultant X, Y, and Z forces of the structural model. By comparing the SCFlow resultant forces to the structural resultant forces, the force losses, my apologies, can be quantified. The one-way analysis was performed using SC Converter. SC Converter is a tool developed by Cradle and is part of the SC Flow Kicker. The tool can be used to map properties such as temperatures and pressures from the SC Flow result files onto different structural meshes generated by MSC Nostran, Abacus or IDEAS. The process can be seen over here. Input for the SC Converter is the Nostran bulk data file, the SC Flow output file, mapping the pressures onto Nostran BDF, creating a mapped Nostran BDF, which can be run in the solver. For the two-way analysis, the CoSim engine uses weak coupling to analyze structural and fluid dynamics. This means that both the Nostran and the SC Flow solver are running when the CoSim is active. The CoSim engine acts as a bridge connecting the two analysis methods. The interactions between the different software applications can be seen in the figure below. With the 2020 release of the CoSim engine, a GUI is provided to start and monitor the progress of the two-way analysis. Before the pressures were mapped to the structure, a CFD warm-up time was introduced. This warm-up time was used to reach steady state for the winglet CFD models. Based on testing, it was found that the flow reached steady state after 500 iterations for both conditions. The CFD warm-up time constraint of 10 hours prevented the cruise condition from running the full 500 iterations. Due to the time limit, the iteration count was reduced to 150 iterations over 13 hours of calculation time. The takeoff condition reached 500 iterations in 9 hours. During the one-way analysis, the start of the two-way analysis was used as a reference point. The pressures found at the start were mapped to the structure and analyzed using SOL 101, linear structural analysis. For the two-way analysis, the comparison was made when the maximum deflection was reached. In this way, the maximum aerodynamic impact of the deflections can be quantified. To find the maximum deflection, the two-way analysis was run for 150 iterations over 1.5 seconds. With the use of the Nostran STS file, the maximum deflection was found for each condition. After doing the analysis, we can compare the one-way to two-way performance. As mentioned, the one-way analysis has been performed using SC Converter as built-in tool with SC Flow. Over here you can see the pressure and the shear stresses in all directions, the SC Flow results and the Nostran results. What can clearly be seen is that we have some deviations between Nostran and SC Flow. What we found was that with the mapping in SC Converter, the shear stress, the wall shear stress, is not considered. As the X direction is the flight direction, causing the biggest difference in wall shear stress, we also saw the biggest deviation. Span-wise, we saw an over-prediction of about 6%, which we can actually not clearly identify. Within CoSim, it can clearly be seen that the results match perfectly. This is a result of the wall shear stress being considered during mapping. It's a force vector mapping, also being able to transfer the in-plane force vectors. The mapping accuracy is to within 100%, so it's identical. A disadvantage, however, is that your CPU time will increase. In our case, it increased threefold. What we also did was the mapping performance with respect to Nostran mesh density. In this case, we only looked at force vector mapping, so not just pressure mapping. SC Flow mesh was kept consistent and the results that you can see over here is that there is near perfect mapping. We identified, or we used three mesh densities with increasing number of elements. Mesh 3 is in the end the mesh we used, but to identify if we could decrease the number of elements, we did a performance study on the mesh density. Over here you can see the comparison of the results, and already for mesh 2 we are within within perfect agreement of results. So now the conclusion of the two conditions. Remember that we looked at two conditions: the takeoff conditions being very heavily involved with induced drag during takeoff and climb. What you actually can see as a comparison between the one-way and the two-way analysis is that there is a delayed pressure peak. The change in the drag coefficient and the lift coefficient is, however, minimal. The maximum wingtip deflection was found after 75 iterations at 2.78 millimeters. The difference between the maximum and the minimum deflection were about 0.02 millimeters, which gave us the idea that we've reached a very good steady state. The pressure contours in the two-way analysis closely match the pressure contours found in the one-way analysis, and the deflections are barely affected by the contours at the wing and the base of the winglet. Nonetheless, effects were seen higher up near the tip of the winglet as pressure increased slightly at the quarter chord, which is around this location. The overall effect of the deflections on the aerodynamic behavior was small. Differences between the one-way and the two-way analysis were minimal when looking at the pressure contours. The other investigated condition was the cruise condition. During the two-way cruise analysis, the maximum wingtip deflection was found at nearly 5 millimeters after 200 iterations. The minimum deflection was found at 4.98 millimeters at iteration 265. From the left cross section in this figure, turn off my pointer. In the left figure, a small increase of the local Mach number is visible over here. The numerical increase was 0.015, so it's not a lot, but you can see some difference between the two. Both areas were already supersonic, both in the one-way analysis and in the two-way analysis. The differences are negligible and have a minimal impact on the overall behavior of the winglet, as can be seen over here for the one-way and two-way analysis of the pressure coefficient distribution. So, conclusions for this part of the research. The research is continuing on, but so far we can conclude a few things, and that's that the two-way analysis has shown that the MSC CoSim engine can handle complex geometry of the winglet. The superior mapping performance of the CoSim engine has been proven, and furthermore, the accuracy of the simulation was increased by considering skin friction during the mapping process. Computational time compared to the one-way analysis is higher, quite substantially higher, obviously. This research has provided insight into the setup of two-way analysis using the MSC CoSim engine. Results show that the engine can perform aeroelastic analysis on complex geometrical shapes and high accuracy models. The superior mapping performance of the CoSim engine has been proven and is something that we will surely continue on using. Improvements can be made actually on the user experience as the user guide was limited for this edition. Future work for these investigations and research is obviously modeling the internal wing structure. What we've done so far, also for reducing the complexity of the calculations, was have a solid winglet. In real life, obviously, you will not have a solid winglet, but an internal wing structure, which actually can also have an effect on the deformation and then on the two-way analysis again. But it's a step that we're going to take. We're also going to do some structural analysis on a winglet. With the release of the CoSim engine 2021, we're going to rerun a few of the analysis in this version. And we're going to do some validation of the other coupling types in CoSim because CoSim can couple other physical solvers like Adams and Mark as well. So what's new in the CoSim 2021 engine? That's new GUIs on the preprocessor side. You have the CoSim Pre-Basic and the CoSim Pre-Plus. Giving you all kinds of possibilities to do very good pre-processing for the CoSim run. There is a new CoSim launcher also to check your run during the analysis, and there is a new Adams SE Stream coupling within MSC 2021. This concludes my presentation. And I would like to open the floor for some questions. Thank you very much for listening, and I will be happy to answer your questions. Thank you.